Okay, I hope my screen is visible. Okay. So we have been looking at source conversions and then mesh analysis also. So just to recall. Okay. So just to recall, in case you have a voltage source with voltage source with impedance in series, you can convert that into a current source with impedance in parallel, and the value of the current source will be the voltage source divided by the impedance. So, and then we did some example also. We started off with mesh analysis too. So in mesh analysis, it is the same. I mean, the rule remained the same. The first thing that you need to do is convert these elements into boxes. In case you have a resistance and any other element in series also, you will combine them also together into one single element. So we will apply block diagram approach, converting this block diagram into this diagram into a block diagram like this. Then you can apply your mesh analysis, Kirchhoff's voltage law in loop 1 and loop 2 separately. You can apply formative approach directly also. So, and once you create the block diagram approach, we will identify what are our impedances in each branch. So in this case, so Z1, Z2, Z3 are the three impedances. We identify its corresponding circuit elements, and then we apply our mesh analysis. Either you can apply formative approach or you can apply the conventional approach also, right? So we discussed about the use of calculators also here. And then we did this example too. I think we ended up our last class in this particular example. Now let us continue with mesh analysis again. So this is the circuit we have, and we need to write just the mesh equations only. So to write the mesh equations, first let us identify the impedances. I think we did this particular problem too. So here, what are the impedance? Now this resistance and inductance you can combine together. So since they are all in series, you can rearrange them in either way, right? So R1 in series with XL1 and then with E1. So Z1 here will be R1 plus JXL1. Z2 here will be R2 plus JXL2, and Z3 here will be minus JXC1, and then Z4 here will be R3 minus JXC2. Z5 is R4 and E2 as it is. So your mesh equations now will be, let me tell you how to write again the mesh analysis. I1 is the loop current in loop number 1 multiplied by the sum of impedances in loop 1. So I1 multiplied by Z1 plus Z2 and minus I2 multiplied by the impedance between 1 and 2, which is minus I2 Z2. And then common between 1 and 3. There is nothing common between 1 and 3. So it is plus 0 will be equal to, as you travel along this particular route, you are encountering minus 2 plus. So it is plus E1 here. It is plus E1 here. So next loop number 2, it is minus I1 multiplied by the common in between 1 and 2, which is Z2, plus I2 multiplied by Z2 plus Z3 plus Z4 minus I3 multiplied by common between 2 and 3 is Z4 will be equal to 0 because there is no voltage sources in this particular loop. So which means just changing the sign throughout. So this becomes, so it was earlier minus, plus, minus, sorry, plus. So now it will be, here it should be plus actually. Okay. Yeah, here it should be plus. So for the third loop, it is I3 multiplied by Z5 plus Z4 minus I2 multiplied by Z4 will be equal to E2, right? So there is a change in this particular sign. This should be plus, this would be plus. So this is the loop equations. Now similarly, let us take another example. Let us write the loop equations for this. Before that, let us identify what are Z1, Z2 and Z3. Now let this be Z1. So Z1 here will be R1 plus JXL1. And let this be Z2, this be Z3 and Z4. Z2 is R2, Z3 is JXL2, Z4 is JXL3. So, and you can, let us assume the current directions in clockwise directions in all the loops. So I1, I2 and I3. So these are the current directions that we have assumed. Now, if we write the loop equations, first let us write the loop equation for loop number 1. So I1 multiplied by Z2 plus Z4 minus the common between 1 and 2 minus I2 Z2 minus I3 Z4 will be equal to plus E1. Okay, will be equal to plus E1. So this cross is nothing but telling the diagonal elements. That's all. It is not striken out, but these are diagonal elements. So now loop number 2, the common between 1 and 2 is Z2. So, and across Z2, I1 and I2 are in opposite directions. So hence it is minus I1 Z2 plus I2 multiplied by Z1 plus Z2 plus Z3 minus common between 1 and 3 is Z3. So it is minus I3 Z3 will be equal to 0 because there is no voltage sources in this particular loop. Now, loop number 3 equation. I1 minus I1 multiplied by Z4 minus I2 multiplied by Z3 plus I3 multiplied by Z3 Z4 will be equal to plus E2 will be the loop equation. So this is how you write the mesh equations, and then you will have to substitute the values and solve for either you should use Cramer's rule. There are or the simplification will get difficult. Now let us apply nodal analysis. Now again, for applying nodal analysis, we will have to first again convert this into a block diagram approach. If you convert this to a block diagram approach, so let this be Z1, this be Z2, and let this be Z2 here, and then this be Z3, and this be Z4. Okay, and what are the nodes here? You have one node here and another node here. So second node here. So converting this into a block diagram approach. So you have this represented as Z1, this represented XL represented as Z2, and Z3 is your R2, Z4 is minus J XC. So let us list the values also. Let us focus towards node number 1. So this is node number 1 and this is node number 2 here. So node number 1, the voltage corresponding will be V1. The voltage corresponding will be V1 for this. And node number 2, the voltage corresponding will be V2 for this. Now, focusing towards node number 1, let us assume all the currents leaving this particular loop. So let this current leave and let this current leave and let this current leave. Now, what will be the, so this is what is the assumed current directions here. So across node number 1, we are assuming that I1 is leaving, I2 is leaving, and I3 is leaving. So this is the same diagram. So we have assumed that this current is leaving, this current is leaving, and this current is leaving. Now, if you write the equations again, let us follow the formative approach. What is formative approach? So V1 multiplied by sum of all admittances connected to node 1. So what are the sum of all admittances? It is 1 by Z1 plus 1 by Z2 plus 1 by Z3. So it is V1 multiplied by 1 by Z1 plus 1 by Z2 plus 1 by Z3, and then the common admittance minus the opposite node, which is V2 here, multiplied by the admittance that is common between 1 and 2, which is 1 upon Z3, will be equal to what is the current entering, right? The sum of currents leaving equal to. So now the current entering will be equal to, it is what is this particular current in this particular branch? It is E by Z1. So it is E by Z1, and why it is, whether it is plus or minus, it depends on this polarity here. So it is, if it is minus and plus, the current is going to come out from this particular current voltage source. Hence, this is a positive polarity. In other words, if you are unable to visualize this, what you can do is, before applying this loop analysis, convert this particular branch into a current source with an impedance. So if I convert this into a current source with impedance, I will have a current source here, and then I'll have this impedance here, right? So Z1, and then I have this V1 here, right? So, or if I can connect this Z1 here and this to ground. So what I'll have is this Z1 will be a part of this particular node, and then this current is entering. And what is the value of this particular current? This current will be equal to E by Z1. So by that way also you can apply. Now let us write the loop equation for, nodal equation for node number 2. So node number 2, so V2 is the voltage. So V2 is the voltage. So what is the sum of admittances connected to V2? It is 1 by Z3 plus 1 by Z4. 1 by Z3 plus 1 by Z4. And the current that is common, the admittance common between 2 and 1 is minus V1 multiplied by 1 upon Z3. So it should be minus V1 multiplied by 1 upon Z3 plus V2 multiplied by 1 upon Z3 plus 1 upon Z4. So so we have assumed that this current is leaving, this current is leaving. We cannot assume that this current is leaving because we already have a current source here. So the actual current source direction we have to consider. So rightly saying, this current source must come on the left hand side because we are writing all the sources on the right hand side. So this will become negative here. So it will be minus I1. It will be minus I1. So just changing the sign throughout. So this can be plus, this can be minus, and this can be plus. Okay. So by this way, you can write the nodal equations. Now, how we will have to calculate these values, right? So to calculate these values, try to find out what are the admittances of this. So we have already taken the values from this one. So what is Z1 here? You need to write somewhere. So your Z1 is nothing but 0.5 and Z2 is nothing but J10, right? So J10, everything is kilo ohms, so we can consider it to be just K. Z2 was J10 and Z3 is again 2 plus J0, 2 plus J0. This also 0.5 plus J0, and Z4 here is going to be 0 minus J5. Okay, 0 minus J5. So with these values, you can use the variable methods in your calculator. You can feed Z1 to be A1. So you can feed Z1 to be, yeah. You can feed this Z1 to be A, this to be B, this to be C, and this to be D, right? So write it somewhere as a rough work and then just feed the values. So let us calculate 1 upon Z1, 1 upon Z2 plus 1 upon Z3. So this value, if you feed it in your calculator, that is inverse of Z1 plus Z2 plus Z3, you get 2.5 angle minus 2.29 degrees. Similarly, the other admittance values, 1 upon Z3 plus 1 upon Z4, it is 0.539 angle 21.8. Now you can substitute these values in this. So it is V1 multiplied by, so V1 multiplied by this admittance together here, and then 0.539 comes here, and then the inverse of Z3 and inverse of Z3. So they all the same, and E upon Z1 you calculate, which is 24 milliampere, and I is nothing but 4 milliamperes we have, which is given. So once you do that, you will have to apply Cramer's rule, and then using Cramer's rule, you can calculate what is this particular value. Again, you will have to use your calculators diligently, or if you don't have that conventional a high-end calculator, then you will have to expand this matrix. So, and then you will have to calculate. So your V1 here is 9.95 angle 1.88 degrees. Okay. Now let's
So
do
we'll have to
another.
expand it in
Yes.
every calculator, right?
Sorry.
We'll have to expand it in every calculator, right?
Um, yes, because this is a matrix. Yes, you will have to expand. We have suggested another method also here, right? So what you can suggest is, so this will be, yeah, so this will be E1, this will be E1, and this will be I1. So, and this will be Z3, 1 upon Z3. So it is nothing but Z3 inverse. So this will be 1 upon Z2 inverse, sorry, yeah, Z2 inverse plus Z3 inverse. So you can feed it as it is in the calculator, and then you can use the calculate button to get these values. Anyway, you will have to expand this. Yes. Yeah. Okay. Now let us take another example. You will have to determine the voltage across this 4 ohms, and you will have to apply nodal analysis. So for nodal analysis, what are the nodes? So this is node number 1, and this is node number 2. And if it is node number 1, the voltage across this will be V1, and the voltage across this will be V2. And considering this to be a block diagram approach, let this be Z1, this be Z2, and this be Z3, right? And let us write the equation. So considering the block diagram approach, I1 is leaving, and Z1, Z2, Z3, V2, and I2 is entering. So what are the values of Z1? Z1 is nothing but R4 plus J0. So always the best practice is write completely, which is 4 plus J0, and Z2 is 0 plus J5, and Z3 is minus J2, 0 minus J2. So having this, you can write now the equation. So this is the nodal, this is the circuit, block diagram circuit. Again, we will assume that the currents are leaving node number 1 and node number 2. So across Z1, your current is going to leave, and Z2 also current is going to leave. So it is V1 multiplied by sum of all admittance. There is a mistake. So it is V1 multiplied by sum of all admittances 1 upon Z1 plus 1 upon Z2. So this will not be there, minus V2, and the common between admittance common between 1 and 2 is Z2, will be equal to, again this current is leaving, so it is minus I1. Now coming to node 2, it is V2 multiplied by Z2 plus Z3. minus V1 multiplied by admittance common between 2 and 1, which is 1 upon Z2. And this current is entering, so it is plus I2. Okay. Now, either you can have it this way as it is, and then you can calculate, or you can determine, you can use admittance also, or convert everything into admittance and then you can calculate. So if I calculate, if I, instead of having it in impedance, I can, if I have it in admittance, then what I will have is, I will have Y1 plus Y2 here. I will have Y2 here. I will have Y2 here. I'll have Y2 plus Y3 here. Y2 plus Y3. So Y1 is 1 upon Z1, Y2 is 1 upon Z2, Y3 is 1 upon Z3. And you will have your expressions as I have written here. V1 multiplied by Y1 plus Y2 minus V2 multiplied by Y2 will be equal to minus I1 minus V1 Y2 plus Y2 V2 plus Y3 plus equal to I2. And again, you will have to apply the Cramer's rule. So if you apply the Cramer's rule, so it is minus I1, I2, don't substitute the values till the end. Then you will can expand this Cramer's rule also. So it is Y3 plus Y2 multiplied by minus I1. Minus of minus will become plus, and I2 Y2 divided by the determinant form. Now always this form looks familiar if you convert these into your alphabet variables in your calculator. Okay, so which means let us assume Y1 to be say A here, this to be B in your calculator, this to be C, and any other variable you have. So let this be D and let this be E, right? So always the pattern remains the same. So this will be, I'm writing it in small letters, A plus B, and then here it will be Y3 is C, C plus B minus B squared. Minus B squared in your, you can just feed it as it is in your calculator. Y3 is minus C plus B multiplied by I1 is D plus I2 is E multiplied by B, right? Mostly this particular form remains the same in your calculators. When you convert for all the problems, if you see here, it is minus of C plus B into D plus EB divided by A plus B plus B plus C minus B squared, right? So let me go to some of the previous place where we have entered this A, B, C, D form. You see here, it almost remains the same. A plus B multiplied by B plus C minus B squared. And in the numerator, it depends on the size of the matrix. So here also, it remains the same. Okay, so almost remains the same. Okay. Now come. Okay. Now, in case you start feeding these values directly, then it slightly gets complicated. So you will have to pluses and minus. You will have problems encountering minus, plus. You know, you will make mistakes. If, for example, you see here, Y3 is 1 upon Z3, which is nothing but capacitance, I believe, right? So it is minus JXC. So Z3 is nothing but minus JXC, which is minus J 2 ohms. So if you substitute, we substitute here, it is 1 upon Z1. So 1 upon minus J 2 ohms, feeding it in calculator this way, putting appropriate brackets is very important. So it is always very difficult if you feed it in an inline form. There are two forms. Either you can write your equations in by fractions or in inline form. So always try to use the fractional mode, as I said in the other class. So just to feed it this way, minus C plus B into D plus EB divided by, so where your A is 4 inverse and B is 5i inverse, C is minus 2i the whole inverse, and D is 6 and E is 4. So if you, these are just a part of your rough calculations. It's not part of your actual calculations. Okay. So if you write this A, B, C, D in exams, I will not be able to give you marks. Okay. So just calculating, just pressing equal to, I was able to get this. So which means our V1 here. So this is in the complex form. So V1 here is 20.8 angle. 126.87. I think it is minus. I'm not sure whether it is plus or minus. Okay. Now, always use the fraction mode in your calculators. So this was computed using the fraction mode. Now let's take another problem. Again, here, what is Z1? So let this be Z1. Let this be Z1. This be Z1 and this be Z2. This be Z3 and this be Z4. So Z1 is R1 plus JXL1, which is 7 plus J8, 7 plus J8, and this be 4 plus J5, 4 plus J5, and this will be 0 minus J10, and this will be 8 plus J0, 8 plus J0. So I'm converting these into the block diagram approach. So Z1 is 7 plus J8, Z2 is 4 plus J5, as we have said, Z3 is minus J10, Z4 is 8. Now, again, in case having a voltage source with impedance creates a confusion for you, you can always convert this into a current source, right? So you will have a current source here. Look at the direction properly, and then this impedance now will come parallel. So this will be Z1 here, right? And what is the value of this current source? This value of this current source will be going to E1 by Z1. So now you can start writing the nodal equation. This is node A and this is node B. And now you can write the equation. So what is E1 here? E1 here is 20 angle 0. And if you convert this, it will become I2 because this is I1 already, which is 10 angle 20. So it is 20 divided by 7 plus J8. So E1 is 20 angle 0 and I1 is 10 angle 20. So this is the diagram. So you can convert this into a current source, as I said before, which will become, so I2 will be equal to E1 upon Z1 and this to be Z1 again, which will come in parallel now. Okay, so this is the voltage source with impedance in series has been converted into a current source with impedance in parallel. Now you can write the nodal equations directly. Either you can write it in terms of impedance or in terms of admittance, whichever suits you. But I always advise you don't use admittance method. So it is V1 multiplied by sum of all admittance. So Y1 plus Y2 plus Y3. Y1 plus Y2 plus Y3 minus V2 common between 1 and 2 is 1 upon Z3. So it is Y3 will be equal to, and this current is entering. So sum of currents leaving. So this part is sum of currents leaving and this is sum of currents entering. So equal to plus I2. Similarly for node 2, sum of all admittances connected to 2 is Z3 plus Z4, 1 upon Z3 plus 1 upon Z4, minus the common between 2 and 1 is Z3. So minus V1 Y3 will be equal to current entered. So which is I1. So by then you will have to substitute these values. I am not going to substitute these values and get. So we have to just write the nodal equations only. Hence, I am not substituting, but you will have to substitute and get the values. Okay. So with this, we are done with the nodal analysis. Now let's move ahead with the bridge networks that we saw. So just as an example, let us take one bridge network, not exactly a Wheatstone bridge, some bridge networks. Okay. Now, how do we start? Again, either you can apply mesh analysis or you can apply nodal analysis, but whatever you apply, first thing that you need to do is combine the convert this into block diagram approach. So if you convert this into block diagram approach, so this becomes Z1, this becomes Z2, Z3, Z4, and Z5. Now, how do you write this Z1? because so this you will have to write. So what if you consider this to be Z1 here? Let me consider this variable to be R1 and C1, right? So let us consider to be XC1. So Z1 here will be equal to R1 multiplied by minus j XC1 divided by R1 minus j XC1 will be this value of Z1, right? Because they are a parallel combination, right? Again, I repeat, this Z1 will be R1 multiplied by minus JXC1 divided by R1 minus JXC1. Whereas this Z4, if you take this R4 and L4 are in series. So it is R4, so Z4 will be equal to R4 plus JXL4. XL4 will be this Z4 combination. Look at the difference here. Okay, so we'll have to be slightly careful. Now, if we apply mesh equations, then you know how many equations are there? There will be three mesh equations here because loop 1, loop 2, and loop 3 equations. So I1 multiplied by Z2 plus Z3 minus the one common between 1 and 2 is minus Z1, and one common between 1 and 3 is minus I3 Z3, which will be equal to, because this is a mesh equations, it will be equal to E, right? So it will be equal to E. Now similarly for loop 2, Z2 plus Z1 plus Z5 multiplied by I2, common between 1 and 2 is Z1, common between 2 and 3 is Z5. So Z5 equal to 0 because there is no voltages in this voltage source in loop 2. Similarly, no voltage source in loop 3. So you get this mesh equation. So this is how you write a mesh equations if you have a bridge network. Now coming to and after this, what you will do, if in case you need to find out the current I2, all you need to do is again you will have to convert this into Cramer's rule matrix method. So converting this into matrix method, it's slightly longer. There is no other option. You will have to expand this. You will have to expand this. So, but most of the cases it will be easy for you because the two elements are 0. So if you consider this column and then multiply, it will be easier for you. So you will have just one element in the numerator. So what is that particular element? So E1 multiplied by uh, E1 multiplied by these Z1 plus Z3. So this and this, right? So Z1 plus Z3 multiplied by these columns. So or E multiplied by, so the combinations Z, so this multiplied Z1 multiplied by Z3, Z1 multiplied by Z4, Z1 multiplied by Z5, and then it is Z3 multiplied by Z5 divided by the whole determinant of this. So the determinant is simply written as it is, but you will have to manually write and then calculate. And in case you need to find out I3, similarly I3 also, it remains almost, it's so the third column gets replaced with E. So accordingly you will have to write. So this is nothing but your mesh analysis. The same problem you can do it using nodal analysis also. So let me take another bridge network. This particular bridge network is known as a Hayes bridge, Hay hyphen S, Hayes bridge. So again, so the input is a current source here. So what are the nodes? You have node number 1, node number 2, node number 3, and node number 4. So these are the 4 nodes here. So if this is node number 1, so voltage across this is V1. If this is node 2, voltage across this is V2. This is node 3, voltage across this V3. This is a ground potential, so this will be 0, right? And again, converting this into a block diagram approach, your block diagram approach, Z1 is going to be R1 minus JXC1, and Z2 is R2, Z3 is R3, Z4 is R4 plus JXL4, and Z5 is R5. Now you can write the nodal equations for this. So how do you write the nodal equations? Again, V1 multiplied by sum of all admittances. So instead of 1 by Z1, you can write admittance Y1, Y2, Y3 also. So V1 multiplied by Y1 plus Y2 and the uh, minus V2 and the common admittance is Y1 and minus V3 common admittance is Z2, which is equal to, and we are going to assume that the currents are leaving all these nodes and here the current is already entering. So current leaving must be equal to plus sign. Here again, with respect to V2, let us assume the currents leaving across these three nodes. So V2 multiplied by Y3 plus Y5 plus Y1, Y1, Y3, Y5, and then common between 1 and 2 is Y1, common between 1 and 3 is Y5. And yeah, now let us write for V3. So assuming currents to be leaving V3, V3 multiplied by Z Y2 plus Y5 plus Y4, 2, 4, 5, minus common between 2, 3 and 1 is Z2. So Y2 common between 3 and 2 is Z5. So Y5 will be equal to 0. Okay. So and then you can apply the Cramer's rule, and please note that all these y's are Z inverse. All these y's are Z inverse. You will have to write accordingly. Okay. Okay. So and then you will have to expand this. So you'll have to expand this again. If you have two elements 0 here, it will be easy. If it is not 0, if you have a current source that is connected to these nodes also, then it will be slightly difficult. Okay. For example, I have a current source connected here, and I have a current source connected here. Right. So these will make things slightly difficult. Okay. So and then you will have to calculate the determinant. You will have to calculate the determinant, and to calculate the determinant, you will have to expand this manually. There is no other option to it. Okay. So similarly, you can find V3 also. Likewise, you can determine the node voltages. Now let's move on to, since we have seen this bridge networks, let us move on to the star delta and delta star transformations. Now, the rule applies the same. If I have a delta network connected between A, B, and C. So what is the delta network between A, B, and C? So between AB, I have ZC, between BC, I have ZA, and between AC, I have ZB. I can convert ZA, ZB, and ZC to Z1, Z2, Z3 by just applying delta to star transformation. So what I want Z1, right? So if I want Z1, so what will be the formula? So my delta consisting of ZA, ZP, ZC is going to be replaced with Z1, Z2, Z3 of a star network. So what is the formula? Z1 is nothing but it is common between B and C. So it is ZB, ZC divided by ZA plus ZB plus ZC. Okay. So Z1 value will be equal to ZB, ZC divided by ZA plus ZB plus ZC. Similarly, Z2, if I want to calculate Z2, Z2 is between two impedance, ZA and ZC. So it is ZA, ZC divided by ZA plus ZB plus ZC. Now Z3 similarly, ZA, ZB divided by ZA plus ZB plus ZC. So this is how you convert a delta to a star. So this formula applies to converting a delta to star. Now, in case you want to convert a star to delta, which means I have Z1, Z2, Z3, and I need to convert this into ZA, ZB, and ZC. So now the value of ZA will be equal to the products actually. So Z2, Z3 plus Z3, Z1 plus Z1, Z2 divided by the opposite impedance that you have. So what is opposite to ZA? Z1 is opposite. So your ZA, sorry, Z, yeah, similarly ZB is opposite to Z2. So ZB, it is Z1, Z2, Z2, Z3, Z3, Z1 divided by the opposite impedance, which is Z2. Similarly, ZA, for ZA opposite is Z1. So in the denominator, you will have Z1 in the denominator. And ZC, in ZC, what is opposite? ZC's opposite is Z3. So in the denominator, you will have Z3. Okay. And again, the special case, what is the special case? If all the impedances values are same. If all the impedances values are the same, for example, the delta, if all the star values are same, Z1 equal to Z2 equal to Z3. So what happens here? So there becomes Z squared divided by 3 times Z, so which is nothing but Z by 3. So your delta value will be 3 times that of Z star. How do you remember this? Is always delta values will be larger than the star values. Okay, so by this way you can remember this. So impedance of delta will be thrice the impedance of your star network. So let's take a very simple example to calculate the impedance of a network. Okay, so we need to calculate the total impedance similar to admittance. So either you can convert this this delta to star, or you can convert this star to delta, or you can convert this star to delta, or you can convert the bottom delta to star also. Okay, now let us convert the top delta to star. So what is top delta? First identify the impedance. What is ZA, ZB and ZC? Let us assume this to be ZA and this to be ZB and this to be ZC. So ZA is minus JXC minus J4. ZB is also minus J4, but ZC is 3 plus J4. 3 plus J4. So if you convert this into a block diagram approach, ZA, ZB and ZC, we are going to convert this into a star network like this. So if what will be the value of Z1, Z2 and Z3? So Z1 is between ZB and ZC. So Z1 will be equal to, the formula will be equal to ZB ZC divided by ZA plus ZB plus ZC, right? So that will be the value of Z1. Now, if you convert this, look at the terminals, which is very important. This is terminal 1. This is terminal 1. This is terminal 1, terminal 2 and terminal 3. We are not going to replace any of these terminals, terminal 1, 2 and 3. Between terminal 1 and 2, we have these star networks. We have these star networks. So your Z1, you will have to replace now. So you will have to replace. Now this Z1, Z3 will be between. So I will have Z1. I will have Z3 here connected between Z2, and I will have Z2 connected between this. So this goes, and this goes. So which means your circuit now will become like this. So Z1, Z2, Z3. Now, what are the values? Let us recall the values of our impedances. Your ZA is minus J4, ZB is also minus J4, and ZC is 3 plus J4. Now, what is the value of Z1? Just the formula. Z1 is going to come in between this, right? So Z1 here. So Z1 is going to come in between like this. So it is ZB ZC divided by ZA plus ZB plus ZC. So Z1 is ZB ZC divided by ZA plus ZB plus ZC. Now, so if you'll have to substitute these values. You can again use the variable method in your calculators. So just to feed this to be A, this to be B, this to be C. Even for small things also you can use the ABC variables, because when you are feeding, this minus and pluses will not create mistakes. So that is the reason. So it is BC divided by A plus B plus C will be in your calculator. So when you calculate the Z1, it is 3.84 plus J 1.11. Similarly, Z2, the formula will be ZA ZC divided by ZA plus ZB plus ZC. So substitute these values, you will have again the same value 3.84 plus J 1.11, and finally the Z3 value. So Z3 is ZA ZB divided by ZA plus ZB plus ZC, and when you calculate Z3, it is minus 1.92 minus J 2.56. Now we have got these values. Now the Z1 and Z4, they will be in series. Z2 and Z4, they will be in series, and that combination will be in parallel, right? So Z1 is given like this, Z3 and Z5, we just calculated. So yeah, Z1, Z2, Z3, Z4, Z5, these are the values. So Z1, Z4, let us consider this to be, say, for example, ZT1. So your ZT1 here is Z1 plus Z4. So just adding this plus this. So it is 5.84 plus J11, 1.11. So will be equal to 5.94 angle 10.76. Similarly, let us consider this to be ZT2. ZT2. So your ZT2 will be Z2 plus Z5. So just adding Z5 plus this. So 3.84 plus 3. So 6.84 plus J 1.11. So converting that to polar, which is 6.93 angle 9.22. Now you have this ZT1 and ZT2 in parallel. So their equivalent, let us assume ZT3 will be ZT1 ZT2 divided by ZT1 plus ZT2. So just putting these into parallel. Again, always use the variable method in your calculators so that you don't go wrong in while even feeding the values. So it's just AB divided by A plus B. So 3.15 plus J 0.56 is the answer. And then the resultant will be in series with Z3. Resultant will be in series with Z3. Your Z3 is minus 1.52 minus J 2.56. So this is the total impedance of this bridge network, 2.35 angle minus 58.41. So the total impedance for this network looking from this side is going to be 2.85 or 2.35 angle minus 58.45, right? So with this, we come to an end on AC circuit analysis technique, that is series and parallel networks. Okay. Now we will have to start with theorems. Okay. Any doubts so far? Okay. Now, as part of network theorems, again, we will be seeing all those 4 theorems that we have started off. What are the 4 theorems? You have superposition theorem, right? So you have superposition theorem. Then after superposition theorem, it is Thevenin theorem, right? So after Thevenin theorem, as a derivative of Thevenin theorem, you have Norton theorem, and after Norton theorem, use of Thevenin theorem, you have maximum power transfer theorem, right? So these are the 4 theorems that we will be looking for AC networks also. Okay, now let us start with superposition theorem. right? You know what is the superposition theorem is? Again, let me repeat quickly. That is, if you want to find a response across a particular element, for example, in this particular case, I need to find out current I, and current I is across this XL2, right? So my response can be either current or voltage. So the response across a particular element, which is now here current across XL2, will be equal to the sum of currents across that particular element when these sources are acting individually. Meaning, that is, I will calculate the current across XL2 using I1 and discarding E2. And then in the next case, I will be using E2 and then I will not be discarding E1. Now, there is a rule also what you should make the other sources. If the other source is a voltage source, you will short circuit that. And if it is a current source, you will open circuit that. So that's the rule of a superposition theorem. So let us solve this particular problem. So using superposition theorem, find the current I through a 4 ohm resistance here, 4 ohm inductive reactance. Again, to start with, convert this into a block diagram approach. So if you convert this into a block diagram approach, let us assume this to be Z1, this to be Z2, and this to be Z3. So your block diagram comes like this, and let us write what are Z1, Z2, and Z3. What is Z1? Z1 is JXL1. Z2 is JXL2. Z3 is J minus JXC, which is minus J3. Now, first we are going to we need to find out current across Z2. So first let us use E1, and what you will do E2, we will short circuit. We will short circuit this. Okay. Now, this is the circuit that you have, E1, and you will short circuit this. So let us assume to be I dash first. So what will be the current? So how do you find the current here? So this is the source current IS1. So you need to, you will have to first determine the total impedance of this Z2 and Z3. So what is Z2 parallel Z3? You will have to calculate. So if you calculate Z2 parallel Z3, so you will have this IS1. So once you have this IS1, you can apply current divider rule, right? And we already know the values of Z1, Z2, and Z3. You will have to apply. But again, always try to use the variable method. It is always easy for you. So what is Z2 parallel Z3? It is AB divided by A plus B. So A is J4 and B is minus J3. You need not type. If you type this in your calculator, you are bound to go do mistakes. So you will type J4 multiplied by minus J3, and if you are using fraction method, it is always easy. But if you are not using fraction method, then you will put slash. And when you are putting slash by mistake, if you write just a J4 plus minus J3, right? With this particular term, only J4 will get divided. So you will have to put brackets appropriately. So that is why I say always use this variable methods appropriately. So Z2, Z3, yes.
So after we've shorted the voltage source, we can use any way to find the current, right?
Yeah, any method you can follow.
For example, even if we wanted to do a mesh here, if we found that easier, we could do that, right?
Yeah, you can do it. Yeah. But here also, if you find mesh analysis, then there are two Cramer's rule you need to apply. Say, for example, you will write mesh I1 here, you will write I2 here, right? And I dash is nothing but I1 minus I2, right? So again, you will have two Cramer's rule. I1 you will determine. So you will have some determinant here, and then you will have I2. Again, you will have a determinant here. You will have to calculate this. You will have to expand this. You will have to find out. You will have to find this difference. So it's a linear method, I believe, but you can definitely follow it. Okay. Now, so Z2, Z3, the parallel value was 12 angle minus 90. Okay, 12 angle minus 90. And then if you expand this, you can find out what is your current IS1. So current IS1 is nothing but E1 divided by Z1 plus Z2 parallel Z3. So it is E1 divided by Z1 plus Z2 parallel Z3, and substitute these values. E1 is nothing but we have, well, what is E1? E1 value was 10 angle 0. So it is 10 angle 0 upon 12 angle minus 90 plus J4 or 4 angle 90. So it is 1.25 angle 90. Now again, you will have to do the reverse calculation going back here. So this value we know, which is 1.25 angle 90. Now you can apply current divider rule to determine the I dashed. So I dashed is nothing but Z3 IS1 multiplied by Z3 divided by Z2 plus Z3. Just applying current divider rule. So substituting this, we will have minus J3. Yeah, so just substituting these values, you will get 3.75 angle minus 90. Okay. Now, so this is I dashed. Now let us look at I double dashed now. For I double dashed, this will be shorted, and then you will have that voltage source here. So you have the voltage source here. Look at the current direction now, because this is minus and this is plus, right? Because this is minus and plus, your current direction is this, and we have shorted this. And your across Z2, your current direction now is going from bottom to top. Again, let's follow the same method. Z1 parallel Z2, rewriting the impedance values. Z1 parallel Z2 will be Z1 Z2 divided by Z1 plus Z2. So which is nothing but calculating it is J2 ohms. Again, you will have to expand this. You will have to find the current IS2 now. IS2 was E2 by Z1 parallel to plus Z3 plus Z3. So which is 5 angle 90. Now we have this particular value, which is 5 angle 90 here. Again, you can apply current divider rule. So IS2 multiplied by Z1 divided by Z1 plus Z2, because here Z1 and Z2 values are same, right? Because you see here, both are J4 ohms. So which means this current 5 angle 90 gets equally divided. So you can simply calculate your I double dash to be half of this. So half of this is going to be 2.5 angle 90. Okay. So 2.5 angle 90. Now so I double dash this 2.5 angle 90, and I dash this 3.75 angle minus 90. So you can, so I dashed is this, I double dashed is this, and I is this. Let's follow the convention. I will be equal to I dash minus I double dashed. So I dash minus I double dash. So which is 3.75 angle minus 90 minus 2.5 angle 90. So calculating this becomes 6.25 angle minus 90, right? So this is how you calculate the current across a particular element using superposition theorem. Any doubt? Okay. Let's take another example. You will have to use superposition theorem to find the current across this 6 ohm resistor. Okay. So you have, so this example covers you have both voltage source as well as the current source. You have both voltage source as well as the current source here. And yeah, converting first attempt, we do the block diagram approach. Convert this into block diagrams. This becomes Z1. This becomes Z1. This becomes Z2. Okay. And this becomes Z3. And okay, so what do? We need to find out this current only. We need to find out Z2. So here Z2 plus Z3 you can consider to be Z2. So 6 minus JXC will be Z2, right? So that makes it simpler. You need to find out the current across Z2. So first let us use, first identify what is Z1. So Z1 is J6 ohms, Z2 is 6 minus J8, 6 minus J8. First, let us use the current source first. So what you will do, the voltage source, you will short circuit it. So with the current source, you will short circuit the voltage source. Now what is I dash? You can apply current divider rule. So I dash is nothing but opposite impedance, which is Z1, I1 multiplied by Z1 divided by Z1 plus Z2. Okay, so that is I dash. So substituting this value, I dash will be equal to 1.9 angle 108.43. Okay, now let us consider E1 now. So what you will do with the current source, you will open circuit this. So you have E1, you will open circuit this. And what is I double dash here? I double dash is nothing but the total current in this circuit. So E1 divided by Z1 plus Z2 will give you I double dashed. So E1 is I double dashed is E1 by Z1 plus Z2. So if you calculate these values, it is 3.16 angle 48.43. Now putting this together, so this is 1.9 angle 108, 3.16 angle 48, and look at the directions. This direction is also flowing in this way. I double dashed is also in this way, and the required current is also in this way. So you will have to add these two things, right? So I is also I double dash, double single dash. They are all in the same direction across the resistance R. So you will have to add this. So just adding this, you have 4.42 angle 70.2 degrees. Okay. Okay. Any doubt? Okay.
So can you show last slide once?
Yeah.
Okay.
Okay. So next theorem that we have is Thevenin theorem. And again, what is Thevenin theorem is any network or any circuit can be simply converted into a voltage source with impedance in series. With a voltage source with impedance in series. So any two-terminal linear AC network can be replaced with an equivalent circuit consisting of a voltage source and an impedance in series. Right. So this is what is the Thevenin theorem says. Let's take an example. You will have to find out the Thevenin equivalent circuit for the resistor shown in this. That is only for the shaded portion here, you will have to find the Thevenin equivalent circuit. So first thing what you will do, you will open circuit the terminals across which you need to determine the Thevenin circuit. So first we will remove this particular part and then we will look from this side and then convert this into block diagram approach. So which means let this be Z1 and this be Z2. So it is Z1, Z2, and so this is how our circuit will be. Now we will have to find ETH, you will have to find RTH. Before that, what is our Z1? Z1 is JXL, which is J8. Okay, which is JXL, which is J8, and Z2 is minus JXC, which is minus J2 ohms, which is minus J2 ohms. Now, okay, now we will have to find our Thevenin equivalent resistor first. So if we want to find Thevenin equivalent resistor, we will look from this direction. And then if you have any voltage source or current sources, we will remove that accordingly. If you have a voltage source, you will short circuit this. If you have a current source, you will open circuit this. So short circuiting this, it's easy to find. So what is ZTH? ZTH is nothing but Z1, Z2 divided by Z1 plus Z2. So your Thevenin equivalent circuit, a shorted Thevenin, it is your voltage source is shorted here, and then your ZTH is nothing but Z1, Z2 divided by Z1 plus Z2. So it is 2.67 angle minus 90. Now again, we will have to find ETH now. ETH, you can use the same circuit here. You can use the same circuit as we have here. Yeah. So you can use the same circuit. Okay. So now what is ETH? ETH is nothing but E multiplied by Z2. I mean voltage divider rule. So E multiplied by Z2 divided by Z1 plus Z2. So ETH is E multiplied by Z2 divided by Z1 plus Z2. And what is this value? This is 3.33 angle minus 180. Now what is the Thevenin equivalent circuit now? Now your Thevenin, now you will have to replace the one that you removed. You as a first step, you removed this resistor. So now you will have to place this resistor after making the Thevenin equivalent circuit. So your Thevenin equivalent circuit now will become ETH, which value is 3.33 angle minus 180, and ZTH, which is 2.67 angle minus 90, and then replace the resistance that you removed already. So you remove this resistor. So this problem can also be a maximum power transfer theorem problem. So for example, let me remodify this problem to be determine the uh, value of the resistor, value of the load resistor. This is a load resistor uh, for maximum power to be transferred across it. So, so, so I need to determine what is this value of this resistance. Normally, now if this is the value of this resistance, this is, we'll not call it as resistance no longer. We will call it as a load impedance. Always the maximum power transfer theorem says that your load impedance must be a complex conjugate of this. So which means your ZL here must be equal to the Thevenin's impedance complex conjugate, which is ZTH complex conjugate. Right? So we'll come back to that later. Okay. Now, having done this, still the problem is not complete. Still the problem is not complete. We have just determined the Thevenin equivalent circuit. Now, what is the actual elements in your circuit? Look at the value. It is 2.67 angle minus 90. Whenever you are having it in polar form, it is always not possible for you to identify what kind of element is that. But in this case, it is simpler because your angle is minus 90 here. So which says that this is going to be a capacitance and its capacitance value is going to be 2.67 ohms. So it is easy here. So your circuit, your block diagram now gets replaced with a circuit which tells you that your ZTH block is XC and it is 2.67 and all the other circuit elements remain the same. ETH is 3.33 angle minus 180. Okay, any doubt? Okay, now let's take another problem. You will have to find the Thevenin equivalent circuit for the network external to the branch A dash. So the circuit here is this. The circuit here is this. What is that you need to find out is you need to find out Thevenin equivalent circuit only between the terminals A and A dashed. So which means first step you need to do is remove this particular part. Remove this particular part from your circuit, right? Now, once you remove this, your circuit will have only the shaded part. And then let us identify what are our impedances. So let us identify this to be Z1 and this combination to be Z2 and this combination to be Z3. Okay. So your Z1 is going to be R1 plus JXL1 and Z2 is going to be R2 minus JXC2, XC actually. Z3 is plus JXL2. So once you have this, let's have the block diagrams first. So our block diagram, once you draw the block diagram, it looks simpler. So your block diagram, it is Z1, Z2 and Z3. So these are our impedance values. Now it is very simple to calculate what is the Thevenin voltage ETH. ETH because there will be no current flowing across this. So there will be no effect of this Z3. So your ETH or EAA dashed is nothing but your ETH, which is nothing but voltage across Z2. Voltage across, sorry, V across Z2. Okay. So what is ETH? ETH is nothing but you can apply voltage divider rule. So 10 multiplied by Z2 divided by Z1 plus Z2. So ETH is E multiplied by Z2 divided by Z1 plus Z2. So again, use the variable method so that it will be easy for you to feed in and get the values. So which is 5.08 angle minus 77.09. Now again, let us still we'll have to find the RTH ZTH value. So for to calculate the ZTH value, what we do? Looking from this side, we short circuit if we have a voltage source. So we are having a voltage source, so we short circuit this. If we short circuit this, so Z1, Z2 will be in parallel, which will be in series with Z3. So your circuit becomes like this. So Z1, Z2 in parallel, which Z3. So your ZTH will be equal to Z3 plus Z1, Z2 divided by Z1 plus Z2. Okay. So your Z3 plus Z1, Z2 divided by Z1 plus Z2. Again, use the variable method. It's always easy to enter the values. So which is equal to 5.49 angle 32.36. Now just remember these values 5.08, 5.49, and we'll have to draw the equivalent circuit now. Now, what will be the equivalent circuit? I have ETH, I have ZTH. So ETH is nothing but 5.08 angle minus 77.09. 5.8 angle minus 77.09. So for ZTH, to identify what kind of element, it is not always advisable to have it in polar form. So convert this into rectangular form so that you can identify what kind of element is this. From the angle itself, you can identify that this is going to be an inductive element. Okay, because this is not negative. So if it's positive, it means that the power factor is lagging, and then it is an inductive element you have. Now, what is that value of inductive element? It will be identified only if you convert this into rectangular. So what does 5.49 angle 32.36 in rectangular form? It is 4.64 plus J2. So what does this mean is, this means that this is the value of resistor and J, this is the value of inductor. At times you will be asked to determine what is the value of inductance value. So you should not give it in terms of XL. You will have to convert this into 2 pi omega L, and then you will have to determine the value of L from this, where omega you can assume it to be 60 Hertz unless otherwise mentioned. Okay. Now replace the removed part. So what is the part that you removed at the starting of your problem? You removed this particular portion, right? You removed this particular portion here. So you replace it back. So replacing it back. So 7 angle 30. Now, again, what is this particular element? It is a resistor and an inductor in series. So resistor, which is 4.64 angle. So the inductor is 2.94. Okay. All right. So this is how you perform Thevenin's theorem from any different circuit. Any doubts? Okay. So we'll stop here and then we'll continue with Norton's theorem in the next class. So you have an extra lecture tomorrow. Just a minute. Let me give you some announcements. Okay. So tomorrow you have an extra lecture Thursday between 3:30 to 5, again online. I'll send you the link. And there will be few more extra additional lectures, almost like till the end of this April. You will have on all Thursdays 3:30 to 5 o'clock, you will have the online class. So we'll be compensating for the classes that I'm going to miss from April 21 to 25. Okay, so we will have compensatory classes. Okay, you may all leave the class.